Okay, we are going to go ahead and get started. Welcome to the Berlin Room. My name is Tim Duvall. Before I get too far into this thing, though, I would like to ask you guys, we've been really popular. This room has, I don't know, I don't know if we're stacked with some of the better speakers or whatnot, but can I ask everybody to move toward the center of your aisle? Get to know your neighbor. Sorry, but hopefully everybody showered this morning. Rub some shoulders if you don't mind. Thanks. Just because we need to get some more people in, and obviously people different sessions are letting out at different times, so we want to get as many people in as we can. As I mentioned, my name is Tim Duvall. I'm responsible for QT in the Midwest. So if we have any Midwesterners, I'm out of Chicago. I've actually seen some faces who have heard this spiel before, so I'll change it up. But if I haven't met you and you're from the Midwest, please make sure you introduce yourself before you leave. Our next speaker is actually going to be talking about changing the design process. He happens to be in aerospace, but I think you'll see some things that are certainly applicable to your day-to-day operations. This is Martin Siggel, and Martin is with the German Aerospace Center. Martin?
Yeah, thanks, Tim, for the introduction. So I'd like to talk about a bit how software actually changed the aircraft design process in the last couple of years, tens of years, and it has had a large impact. And I'm from German Aerospace Center, which is kind of the German NASA, much smaller, but similar like this, so it just that you have a rough idea. So in my talk, I'd like first to talk about how aircraft are designed traditionally, and then I'd like to talk about what software actually enables us to do now, and I'd like to show you some design projects at the German Aerospace Center, which I am also involved. Then the tools we are developing in order to do that, and some of these tools are also built with Qt, and I will show you these things. So let's start. So traditionally, aircrafts are designed in 3 phases, and the first phase is the conceptual design phase, and you really start with pencil and paper and start sketching something. And what you see here is a sketch for the XB-70 bomber. That's a strategic bomber which the US government required at some point, I think in the 60s, which should be hypersonic, which should carry nuclear weapons. So that was one of the first designs, actually. And of course, it looks a bit strange, but this is an iterative process, of course. So you're starting with something, then you're computing something, calculating something, and you improve your design. This is what it later looked like. And this was finally handed into the US government. And in the end, it looked like this. A bomber with a speed of Mach 3, so 3 times the speed of sound. Really an impressive thing. So this is the first step in the aircraft design, doing some sketches. But it's not only, you have to do also some computations. And traditionally you have some collections and books of simple equations which are particularly useful for traditional designs, and which are based on simplified physics or empirics, just measured and fitted some data, and they give you rough estimates of the amount of lift. For example, you get the forces on the wings, the structural loads, the total mass, for example, or tank sizes. But as you can guess here, these are really simplified things, so you have large errors and you cannot really squeeze everything out of these things. And interestingly, what I always seen is or when you start as an engineer, what do you think? What's the main programming language engineers are using? C++ is not the answer. It's Excel, actually. Yeah, I've seen aircrafts which are completely designed in Excel. And you can do a lot of funny things with it I didn't know, actually. It's interesting. But so, this is the kind of thing we're talking about, which happened a couple of years ago. The next phase is preliminary design. So you have some rough idea, and you start creating your models. And then you put them into wind tunnels. And interestingly, even the Wright brothers, with their first aircraft, they started with a wind tunnel, because they've seen that somehow their measurements didn't fit their expectations. Their lift was only a third of them what they expected, actually. So they started building their own wind tunnel, and then they tried to figure it out. But what you can do in a wind tunnel is you can visualize the air streams around the aircraft. You can find out where you have vortices, where you lose some efficiency, and so on. It's a really important tool. But of course, these experiments are expensive, right? Wind tunnel experiments are really expensive. There's a huge machineries, these wind tunnels. And the third design phase is actually you create prototypes and you perform test flights. And this is even more expensive. And here, just some examples. The X-1 was the first rocket-driven aircraft which was faster than the speed of sound. And the X-15, flown by Neil Armstrong, by the way, achieved Mach 7, so 7 times the speed of sound, which is the record. Even today, no aircraft was faster than this. But as you can guess, this is really, really expensive, and none of these aircraft managed to get like a product. So you try to avoid as much as you can building prototypes just for concepts, right? So let's come to the second part, software-enabled aircraft design. What you can do with software is you can analyze unconventional designs, because building aircraft prototypes is too time-consuming and expensive, and software allows you to find strengths and weaknesses of your designs, and you can simulate if all the requirements you get are met. You can explore different concepts, and you can even simulate unconventional designs accurately where no expertise for humans is there, because you have the right tools. What you can also do is you can analyze conventional designs, because you want to improve fuel efficiency, you want to squeeze all the margins, you want to improve reliability and safety. But of course, since conventional designs are there for really many years, there's not much to gain, actually. To get just a few % improvement, you need optimization software which tries to find every configuration and tweaks everything a bit in order to get a few tiny %. So you need really good tools in order to do that, right? So let's come to some design projects at the German Aerospace Center. And I'd like to introduce first the German Aerospace Center here. It's founded by the German government, and we have 5 major research areas: aeronautics, space, transport, energy, and security. But you might ask yourself, where's the software? Actually, software is one major part in each of these disciplines, but it's not a research area by itself. And one of these projects where I'm also involved in is the project Freaks, where we want to find the aircraft of tomorrow, new aircraft designs, unconventional and futuristic designs. For example, here in the front you can see the blended wing body design, which is good in order to to fit many passengers into one aircraft, and which is really efficient in its lift and so on, or strut-braced wing design. And this project is about tracking uncertainties through simulation chains. So typically you have many different software tools, one tool for this discipline, one tool for another discipline, and you want to find out, or each of these tools has some uncertainty, some error in it, and you want to find out how this error propagates through all these things, and what is your error in the end, so to say. Another project is called Digital X, and here's the main target is to perform a complete simulation of the aircraft and also of helicopters with very high accuracy and small errors. And here we want, for example, to improve the fuel efficiency, and we want to fly the aircraft prior to the first flight in a flight simulator. So we want to simulate every aspect of the aircraft and then replicate it in a simulator and to figure out how it behaves. We developed a new fluid dynamics code, so that's the aero code for the aerodynamics, which is using high-performance computers and has massively parallel data structures in it. in order to run efficient, and still it takes a lot of time to do these aero calculations. Another project is the project Mephisto, where it's more about unmanned combat aircraft, so to say drones, where we analyze novel flap and aileron concepts, so that these are the flaps, so to say, at the end of the wings, where we also want to explore new stealth materials, and for example we want to compute the probability of detection by radar or by infrared things, and we want to minimize this probability. This is also a different aspect, right? And now let's come to the tools which enable us to do these things. The most important tool probably is the aerodynamics simulation. So you want to find out how's your aerodynamics, where do you get the vortices, and it's what you're doing is you have some large equation, the Navier-Stokes equations, and you're solving this equation massively parallel with high performance computers, and still it takes a lot of time to do that. But it allows you to really find out the whole aerodynamics without making wind tunnel experiments, which is even more expensive. Then what you also can do is you can simulate the aircraft structure. So what happens when you put mechanical loads onto the wings and onto the aircraft structure. It allows you to estimate the aircraft structure mass, and you can simulate how the wing deform when you put forces onto it. And as you can see here, really interestingly on the right, that is the aircraft Helios, which had so large wings that they bended up really much and also were vibrating. And in the end, actually they broke the wings and the aircraft crashed because in the design process something was wrong. Probably this simulation was not right. It's not an aircraft bias, but this happens when you're doing it wrong. And of course you can guess when you change the form of your wings because of these loads, it changes the CFD simulation, so you have to go back and have to recompute the CFD and so on. So it's a coupled system. It's not everything on its own, which makes it even more complicated. And then of course there are the engines, right? We don't have a glider, so what we can do is we can precisely simulate the aircraft engine. We can simulate the behavior of the engine. We can find out the airflow in the engine. We can simulate combustion. We can also simulate the acoustics, so the noise, so to say, the engine makes, and can minimize it, for example. And we can optimize the engines for a specific requirement. Also, another tool is the dynamics and control software, which allows to simulate how the aircraft moves when you push the stick, so to say, and where you can estimate the forces during maneuver. And it allows you to figure out whether your aircraft behaves as you've originally planned. So, as you can guess now, we have different disciplines. We have the engine makers, we have the structure people, we have the aeros people. And if you ask them what's the optimal aircraft, you can get different answers like here, right? The aerodynamic people, they just want to have the wings. Fuselage is not good. I mean, it's and so on. So, but what we want actually is we want the optimal aircraft in its whole. So what we need is another software which puts everything together, which we are developing. It's called RCE, an open source software, and it's a framework to integrate all these different kind of softwares to one thing together, and it provides workflow management to couple these simulations. And typically you have these different tools running on different locations, and for example NASA has different locations, and German Aerospace Center as well. So it makes network connections, sends the data from one tool to another tool, performs some simulation, sends it back, and so on. And it allows also you to use high-performance computing facilities. And just here as an example, this is a simplified workflow. All of these boxes are tools running somewhere, and this whole workflow takes 45 days. So it involves some optimization, to figure out, here in that case, how can we improve fuel efficiency. And to do that by hand, it's not going to work. So you need something which puts everything together. And this is how it looks like. This is also just some simplified workflow here. Each of these boxes is a tool, and one tool is running at a time, or sometimes even in parallel if it's possible. And it sends the data back to another tool, and you can also see a preview of the current configuration. And you can see how it changes in time. Really practical. So now let's come to the last part, the tools which are built with Qt. One really nice tool we were developing is GTlab. It's a software which allows you to design aircraft engines. It's interactive, cross-platform using Qt, and it allows you to create aircraft engine and gas turbines. And it has 3 major parts, each of these parts reflecting the aircraft design process. And the first part is GTlab Performance. Then we have the Sketchpad and GTlab Pre-Design. Performance looks like this. So it allows you to make thermodynamic analysis of the combustion process and of the whole engine process. You can just plug and play, plug all these parts together to one engine, do some simulations, and you instantly know the behavior, the rough behavior of the engine. So this is the conceptual design phase of the engine, so to say. Then we have the Sketchpad, where it's just more detailed. That's just a sketch through the engine, and you have the possibility to add blades and different parts to really be precise on what the engine should look like. You can have a look in 3D, then you can compute the properties of all these parts, the different parts. You can, for example, compute what the weight of the engine is, because you have everything in 3D. You can even export it in 3D for different programs to render it, for example. And finally, we have the pre-design module, which allows you to be even more specific, to tune all the channels in the engine, to plug different computation models together, like in the RCE program I just shown. So what you can do is you put 2 plugins together. You say, okay, this one output of the one program is the input of another program, and you do some simulation, and you can visualize also the results here. And what you see here is, for example, the velocity of the airstream going through that channel in the engine. Another tool is the TiGL library, which also I am developing. It's a central geometry library used by different simulation tools in German Aerospace Center, because we have a descriptive format called CPAX, which describes in a parametric way how the aircraft looks like, the geometry. And this library creates the 3D model of it, of the whole aircraft. And different tools, aerodynamics, the structures, radar tools, are all using the same geometry by calling this library. It's multi-language, so we support different programming languages. It's multi-platform. It's open source, by the way, and it's based on a CAD kernel, also for computer-aided design, called Open Cascade. And so you might ask, what about Qt in that way? Because we also have a viewer which is visualizing this geometry, and it's platform independent. We support Android, Mac, and Windows, and even iOS, but Android, I mean. But Android is not written with Qt. It's Android native with a C++ part under the hood, at the moment at least. And finally, we have the software called DataFinder. It's not about simulation, but storing the simulation data, which is also important. And so it's a data management software, and you can add tags to your simulation data, and you can search for it. It has a web dev backend where you put all the data on it, and it's implemented in Python and Qt, so we're using PyQt. It's also open source. You can find that under this address. And this is how it looks like. Really simple user interface with all the entries in your database. And we have some wizards which allow you to enter these data. And then we have some web front end where you can access these data. So to wrap up, we have the vision for the complete digital aircraft. We want to simulate everything of the aircraft, but as you can imagine, for example, here, if you have 15 different flight points, 100 mass cases, 10 different aircraft configurations, 5 maneuvers, 20 different gust things, so winds, and 4 control laws, meaning 4 different modes of the flight computer, you end up already with 20 millions of simulations, right? The current engineering expertise is only 100,000 simulations roughly, so there's a large gap in between. So this is why you need software in order to do that, to do the whole analysis of an aircraft. So what I've shown you is software technology which is using also high-performance computing hardware and algorithms which have large impact on aircraft design. And software is nowadays used in all the phases of aircraft design. And still a major challenge is the simulation of the whole aircraft. I think we have some time for questions now.
Absolutely. Any questions?
Yes.
I was curious, what version of PyQt are you using for the one tool you shared? I believe it was the viewer or something?
It's 4 dot something. It's not the 5 version. It's not ported yet. Yeah.
Probably 4.8.
Yeah, probably.
4.86.
Yeah.
It's a long-term release.
Yeah. We started with actually PyQt 3 at several years ago, and we ported to 4, but to 5 we didn't make it.
Any other questions? All right. Well, if a question does occur to you, keep in mind that we will be down in the reception area at 6 o'clock, 6:15, I guess, is when the reception starts this evening downstairs. Until then, my name is Tim Duvall, and if I haven't had a chance to meet you, I would love to. But thank you so much for joining us for this breakout.